Hello and welcome all of you to this session of Applied Thermodynamics. In the previous lecture, we had seen how the Carnot's theorem can be applied to identify that reversible engines has the highest efficiency among all possible engines. Now you know that we have discussed the concepts about the irreversible process and the reversible process. You must have understood that practically in reality there is no such reversible process possible. Now still we assume, we idealize, or we conceptualize the reversible process because reversible process gives us the sense of maximum efficiency. So reversible processes or reversible engines provide us the sense of maximum which we can achieve. As you know, according to the Kelvin Planck statement, there has to be some amount of heat rejection always. It always gives us the sense the efficiency of a heat engine cannot be 100%. In any case, the efficiency of a heat engine can never be 100%, but still you can identify, you can sense, then you can identify the maximum efficiency which is achievable. And again we come to the concepts of reversible engine, which is a maximum possible efficiency which can be achievable. But in reality we can't achieve that much efficiency also, because reversible process is an idealized process. It means that it cannot be never achieved, but it is the maximum possible efficiency ever. Okay, so with this understanding, let us see a corollary of the second law, which we call as absolute thermodynamic scale of temperature. So we'll draw a heat engine, a brief diagram of a heat engine, and we will move forward with the discussions. Okay, so what do we mean by absolute thermodynamic scale of temperature and all? So let us see that. So here we can see a brief diagram of a heat engine. Now in the Carnot's theorem, it was specified that reversible engines will have the maximum efficiency compared to any other irreversible engine which is working between the same temperature limits. So if you try to understand this statement in a different way, you can say if the temperatures are fixed, then then any reversible engine will give you the maximum efficiency. So can we say that the efficiency of a reversible engine is a function of the temperatures? That means the temperature of heat addition. This is the temperature of heat addition, and this is the temperature of heat rejection. So I think according to the Carnot's theorem, according to the first statement of the Carnot's theorem, we can easily say that the efficiency of a reversible engine is a function of the temperatures of heat addition and the heat rejection. So if is it so, then we can write efficiency of reversible engine is a function of heat addition, that means the temperature of the source, and this is your temperature of the sink, or in other words we can say it is the temperature of the heat rejection. So this means you can understand easily that these are the two temperatures by which the efficiency is dependent. Okay, now by virtue of the uh, definition of efficiency for a heat engine, you know that for the reversible engine or for any irreversible engine, you can write efficiency is nothing but the ratios between the work output and the heat input. So this is your output here, that is the work done by the reversible engine, and this is your heat input here, so it will be Q1R. Okay, so and again if you follow the energy conservation principle, then you can write this WR is equal to Q1R minus Q2R. That means heat added minus the heat rejected to the sink gives you the work output. So you can write it Q1R minus Q2R divided by Q. I'm sorry, I will rewrite it once. It will be Q1R. So it gives you, ultimately it gives you Q2R divided by Q1R. Okay, so this efficiency can be represented by this formula. So this formula is valid for reversible as well as irreversible heat engine. So this is a general formula. Now can we write this function? So can we imply that this this ratio or this derivation, whatever you say, this is a function of T1 and T2? Can we write that? Because we have already proved that this efficiency is nothing but 1 minus Q2R divided by Q1R. That is 1 minus the heat rejected divided by the heat received. So we can write now this function T1 T2 is equal to, that means what I am trying to say is that this terms, this Q2R divided by Q1R, they should be a function of the temperatures of heat addition and the heat rejection. It is very easy to understand. And finally you can say, you can neglect this one, so you can say that the ratios of heat rejection and the ratios of heat rejection and heat addition would be a function of the temperature of heat addition and the temperature of heat rejection. So now we would see a different case where we'll see two engines, they will be working in a series, and we'll try to understand the implication of this formula which we have just now derived, which we have just now understood. We'll see how does this formula can be implied for the case when two engines, two separate reversible heat engines, they are working in a series. So let us see that. But please keep in mind this, we have already deduced that the ratios of heat rejection and the heat addition is a function of the temperature of heat addition and the temperature of heat rejection. So keeping that in mind, let us move on to the second case. Okay, so I'll draw the diagram here and I will explain you now. So here we have taken two different reversible heat engines and they are operating in a series. The first one, the reversible engine A, it is receiving heat from this source at temperature T1. The heat which it is receiving is Q1, and it is rejecting heat Q2 to the sink, which has a constant temperature of T2. Now it is producing work WA, which can be calculated from the energy conservation principle as WA equal to Q1 minus Q2. And if you see the second engine, you can see that this thermal reservoir acts as the common sink and the source. So it is the sink for the heat engine A, and it is the source for this heat engine B. So this heat Q2 is the common heat, okay, which is being transferred to this reservoir, to this thermal energy reservoir. Okay, so as you can see, two different heat engines, two different reversible heat engines, heat engine A and heat engine B, they are now operating in series. The heat engine A is taking heat from the high temperature source, which is maintained at temperature T1, and it is rejecting heat Q2 to the sink or the thermal energy reservoir, which is maintained at a temperature T2. Now you can find here this work done or the work produced is equal to Q1 minus Q2. By the from the energy conservation principle, you can easily understand that. Now for the second engine or the engine B, you can see it is taking the heat which has been rejected by the heat engine A. So this heat Q2 is now common. That means it is the rejected heat by engine A, and it is the heat which is being received by the heat engine B. And after receiving the heat Q2, this heat engine B is now rejecting heat Q3 to a thermal energy reservoir which is maintained at temperature T3, and it is continuously producing work WB, which is equal to Q2 minus Q3. Now from the understanding which we have just now we have discussed, we can say the ratios of heat rejected and the heat received can be expressed as the functions of the two temperatures. That means the temperatures of heat addition and the temperatures of heat rejection. Now for this engine A, can we write, I think it will be easy to understand now, this Q2 by Q1 now can be written as function of T1 and T2. Okay, so this is our previous understanding, and for heat engine B we can write Q3 divided by Q2 as function of T3 and T2. Okay, so we are following the same logic, same pattern of logic is followed for these two deductions. Okay, now as you can see here, this heat Q2 is the source for this engine. We can say that this reservoir is acting as a redundant, or you can say this, there is no application of this reservoir, so we can remove this thermal energy reservoir, and we can draw, or we can see the modified diagram here. Okay, so these two heat engines are now in parallel, but they have their this heat engine A has its source T1, which is at temperature T1. This is obviously a constant temperature, and it it will have its sink as T3 temperature. That means these two heat engines, heat engine A and heat engine B, they have common source which is maintained at a temperature T1, and they have a common sink which is maintained as a temperature of T3. Now, say if we write, if we are willing to write this same equation for this set of engines, then how we can write? We can simply write Q1 by Q3. So this is, so this is Q1 by Q3 will be simply function of T1 and T3. Okay, so we are following the same logical pattern. Okay, so there is no change here. Now if we try to establish a relationship between this function and these two functions by simply doing a mathematical operation, right? So we can say Q1 by Q2, we can write simply we can write as mm, we can write so okay, this q1 by q2 can be written as q1 by q3 into q3 by q2, right? This is simple mathematical operation, and I will be clearing up this drawing because this will be not required now, and it will give me some space to explain here. So now here you can see this is your expression which you can find out easily. You can easily understand. Now if you want to find this ratio, this q2 by q1, then what will happen? Simply it will be a little bit of you need to modify this expression a little bit so that you can write q2, you can write simply q1 by q3. I'm very sorry. You can write uh, q2 by q3 into q3 divided by q1, or you can write in this term, you can write divided by q1 by q3, right? So now you can say this q2 by q1, or in other words you can express it as q1 by q2 also. So this will not create a little this will not create some confusions, I hope. Okay, so q3 and q1. Now our we are willing to find a relationship between these three separate functions. Okay, this function, this one, and this one. Since q2 by q1, it can be expressed as q3 by q1 divided by q3 by q2. We can write this f of t1 t2 as f of t1 comma t3 and f of t2 comma t3. Okay, so we can write this. Now the basic understanding from the Carnot's theorem is that if you fix the temperatures of heat addition and rejection, then all the reversible engines will yield the same efficiency. All the output of the reversible engine, all the reversible engine will have the same work output if you fix their working temperatures. So now it is quite understandable, it is quite evident that this efficiency of these reversible engines, they depend on these temperatures. Now how many temperatures are there? There are only two specific temperatures, but here we can find it is getting complex because we are having three separate temperatures. Okay, so it is not as much it is looking like it is not as much as complex. Okay, so and the information which we have understood is that it will be always dependent on the two specific temperatures. So we can write this function of t1 minus t2. The simplest solution in this case would be function of t2, t1 and t2 should be expressed in this format. So this is the simplest solution. Okay, and this, if this relationship doesn't hold, then what will happen? If this relationship doesn't hold, then what will happen? This 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 relationship will not be applied here. It cannot be applied. Okay, until and unless the relationship between these two temperatures are expressed in this format, this relationship cannot be fruitful, they cannot be generated. So this is the basic and the simplest solution which we can achieve, and consequently we can say now that these ratios, the ratios of heat transfers, should be ratio should be equal to the ratios of these two temperatures. So this is our finding, and this is what we mean by absolute thermodynamic scale of temperature. This representing the heat transfers in the format of temperatures. That is what generates the concept of absolute thermodynamic scale of temperature. Now this relationship is our result. This is our final result. And remember, this is only valid for reversible process. Okay, so this relationship cannot be applied for the irreversible cases. Okay, so this relationship, once again I am saying, please remember it, please don't forget ever. uh, so this is for reversible engines or reversible processes. Okay, so I would prefer to write process here. So this is what we find for the reversible process. Now, after understanding this relationship, the formulas of efficiency for a heat engine and the COP for the heat pump or refrigerators can be rewritten. Okay, so let us start with efficiency. So this is eta. Okay, I will rewrite it so that it can be clearly visualized. Okay, so eta is the efficiency for any heat engine. Okay, it is the efficiency for any heat engine, 1 minus q2 divided by q1. So this relationship is valid for reversible as well as irreversible cases. Now, if we are specifically mentioning that a reversible heat engine is in operation, then we can write this 1 minus q2 by q1 can be also written as 1 minus t2 divided by T1. Okay, now let us consider COP. COP of a heat pump. So the general formula to express the COP is that Q1 divided by Q1 minus Q2. Remember that I am expressing all the formulas in terms of the heat transfers. Okay, so this is why this work output terms or the input terms are not involved here. So this is the formula of COP of a heat pump for uh, any cases. You can apply this formula for both the reversible cases as well as the irreversible cases. Now, if we specifically mention that it is a reversible heat pump, then what will happen? We can, along with this formula, along with this relation, we can also write this. Okay, along with this formula, we can also write in the temperature format. Okay, similarly for refrigeration, for a refrigerator, the general formula, it is Q2. It is a low temperature heat, if you remember. So heat pump deals with the high temperature heat, and generally we denote this high temperature heat by Q1, and this is your low temperature heat. Okay, so what I had written, this is your formula, this is your general formula. That means this formula can be applied for both reversible as well as irreversible cases. Now when it is mentioned that a reversible refrigerator is in operation, then along with the formula in the heat transfer formats, you can write this also in the temperature format. So this is how the formulas of the refrigerator in reversible cases can be uh, rewritten. Okay, you can see for this formula is for reversible heat engine. This is for reversible heat pump, and this is for reversible refrigerator. Okay, so this is what we got from this absolute thermodynamic scale of temperature, and we modify the formulas for the reversible cases. So this is our finding. Now suppose in a certain case, this q2 becomes 0. Okay, if this q2 becomes 0, then this T2 would obviously be 0. That means we can say when the heat rejected, this is our heat rejected here. When this heat rejected, let us not take it perfectly as 0. Let us assume that it is tending towards 0. Or we can say this heat rejected is approaching 0. Then we can say this T2 would also approach 0. Now, in real cases, we can say this cannot happen. This T2 cannot be 0. This Q2 cannot be 0, because we know there is already a restriction from Kelvin Planck statement that there has to be some amount of heat rejection always. Since there has to be some amount of heat rejection, this Q2 cannot be ever 0. So what we can say? Uh, we can say that in the absolute thermodynamic scale, a 0 point of temperature, or a definitely we can say that a definite 0 temperature point can exist. Okay, but it cannot be reached because there will be a violation of the Kelvin Planck statement, or specifically there will be a violation of the second law of thermodynamics. Okay, so now with this understanding, let us try to define what the third law of thermodynamics is. Okay, sorry. So we can say thus any attainable value, that means the temperatures which we are talking about, the temperature of heat rejection should be always greater than 0. Okay, so from this we derive the concept of this third law of thermodynamics, which states that it is impossible by any procedure, no matter how idealized, to reduce any system to absolute 0 of temperature in finite number of operations. That means however you try, whatever processes you apply, you cannot make the heat rejection as 0, and you cannot uh, convert this temperature of heat rejection into 0. So this absolute temperature of heat rejection cannot be 0 ever. Mind it, we are talking about the absolute temperature, which is in Kelvin. Okay, so with this understanding, let us move on to the concept of Carnot cycles. Okay, so this is your Carnot engine and Carnot cycle. We'll be explaining it. Okay, so after the concept of the reversible heat engine was developed, it was well defined that reversible heat engine will provide you the maximum efficiency of all engines. Okay, since there is always a restriction that there has to be some amount of heat rejection always, the efficiency of a heat engine cannot be cannot be 100%. And you know that among all the possible reversible heat engines, I am talking about conception, I am talking about hypothetical conditions. Okay, so among all the possible heat engines, reversible heat engines will have the maximum possible efficiency. Now, Sadi Carnot, a French physicist and engineer, he tried to develop a reversible heat engine which would provide you the maximum efficiency. So he conceptualized a heat engine which will almost work in the reversible fashion so that it can provide you the maximum efficiency. But it has to be noted and it has to be informed that this Carnot cycle is hypothetical. It doesn't work in the practical cases. But ideally, conceptually, it is the base of thermodynamics. It is the base of all heat engines. From this conception, from this idea, from Sadi Carnot's idea, the concept of heat engine evolved. The concept of achieving the maximum efficiency possible. This journey evolved from the perception of Sadi Carnot or the Carnot's engine. Okay, so let us try to understand how Carnot conceptualized his engine, which you know as Carnot's engine. So before that, so and along with the understanding, we shall try to derive the Carnot cycle in the PV coordinates later on, but let us see what Carnot tried to do. So let us first write down all the processes, all the thermodynamic processes involved in it. So here you can see all the four thermodynamic processes involved in the Carnot cycle. So pardon my handwriting. So the first process is the reversible isothermal heat addition. Now, so this is a very important concept which you must understand. Here I can see the process is isothermal. That means temperature remains constant, but still heat addition is taking place. Now how it is achievable? And another thing is that it is also reversible. Now from our understanding of the previous lecture, we know that we can only conceive a process as a reversible process if the temperature difference between the system and the surroundings is very low, that is infinitely small. So now if we consider that the initial temperature of this piston cylinder arrangement, or we can consider the temperature of the gas which is confined within the cylinder is maintained at T1. Now what happens, this this piston cylinder arrangement is now placed in the contact of a reservoir which has a temperature of T1 plus DT1. Now this DT1 is the infinite small temperature difference between these two. Okay, so this is your temperature gradient by virtue of which heat Q1 is getting transferred into the gas. Now since heat is getting transferred into the gas, it is quite evident that the temperature would rise. Okay, but still here it has been mentioned that it is an isothermal process. Now how you can achieve, how you can prevent the rising of this temperature, how you can prevent that the temperature of this gas doesn't raise. Okay, so that's why you need to conceptually you need to slowly move this piston so that the gas can expand. Okay, so simultaneously there are two things happening. Heat is coming into the gas, and as the heat is coming into the gas, you are starting to move this piston in this forward direction, which is causing an expansion of the gas. So this expansion is keeping the temperature constant. Okay, and then when heat has been added, there is a movement of the, you can see the movement of the piston here. That means heat has been added and the piston has moved. Okay, now you can easily identify that there will be a temperature the temperature is maintained constant because of the isothermal condition mentioned here. There will be an expansion of the heat addition, the gas will expand. Okay, now so here you can see these dotted lines, these hashed lines, they indicate that the lateral surfaces of the piston cylinder arrangement have been insulated. Heat is only passing through this diathermic wall. Okay, here the pressure and the volume of the initial condition have been mentioned as PAVA because it refers to the state A, and then you can see the piston has moved forward in the forward direction. Okay, now the piston cylinder arrangement is completely insulated. That means now an adiabatic process will take place. An adiabatic expansion process will take place. Now you know what do we mean by adiabatic process. It means that there will be no external heat transfer. Okay, so insulating all the possible walls of the cylinder piston arrangement, we can see the gas is expanding and an adiabatic expansion process takes place. This is obviously a reversible process. In Carnot cycle, all the processes are reversible, and because of the Carnot's theorem, you know that reversible engines will give you the maximum efficiency. This is why this all the processes have been idealized as reversible. Now we are moving on to the next process. Here you can see this is the change of states. This A to B because of the isothermal heat addition, and this is B to C because of the reversible adiabatic expansion. Now the heat rejection takes place. Now again it is easily identifiable. If heat is getting rejected, then the temperature will obviously drop, but you need to prevent this. So because of your isothermal condition maintained here. Okay, so what you will do, you will, when the heat is getting rejected, you will slowly, very slowly, you will compress the gas so that the temperature is maintained at the same. So the temperature is maintained constant. Okay, in the first case we are slowly expanding the piston so that the temperature cannot be varied, so that the temperature can remain constant. In the case of isothermal heat rejection, we are doing the opposite. We are slowly compressing the gas so that the temperature remains indifferent. Temperature remains constant because the isothermal condition has to be maintained. Okay, so isothermal condition means the system and the surroundings, they will remain at the same temperature. Okay, that doesn't mean there shouldn't be a temperature difference. A temperature difference will be always present so that heat transfer can take place. Okay, now moving on to the last process, you can see an adiabatic compression here so that the uh, piston can reach its initial condition, as well as the gas can also reach the initial condition. Here you can see this is the fourth process, reversible adiabatic compression. So with this we sum up the Carnot engine, the four processes which are involved in the Carnot engine. Okay, now if we wish to plot these four processes in the thermodynamic diagram, then how it will be? So let us consider this is our first state, that means the state A, and you can see since there is isothermal heat addition in the first place, that means this is your first process here, reversible isothermal heat addition, then you can easily plot a line like this. Okay, so this refers to your first process in the Carnot cycle. Okay, so now let us move on to the next process where the adiabatic expansion is taking place. And again you can draw this curve would be much more steeper. Okay, so this is your second process C. Then it is the rejection takes place, and then so let me write as this state D, and then your final process takes place. Okay, pardon me for my drawing, you will find it in a much better way in your school books. Okay, so please check it and you will find the diagram uh, in a very beautiful way there. Okay, but for your understanding this diagram is enough, I think. So this is your pressure axis and this is your um, volume axis. Okay, so this is the first process, the reversible isothermal heat addition. That means there is a little bit of expansion, heat is being added, and the states changes, the states change A from A to B. Then because of the reversible adiabatic expansion process, you can see you can see that there is an expansion taking place, and this expansion is mentioned here from state B to state C. Then what happens? Then reversible isothermal heat rejection takes place. So because of this heat rejection, this is your process here. Okay, and then the final one, so that the cycle can be completed. This is the reversible adiabatic compression. Now how you can calculate the efficiency of this cycle? How you can calculate the efficiency of the cycle? Okay, so this is your first process. That means the reversible isothermal heat addition. That means heat is added here. So let us assume Q1 heat has been added here. Okay, now this is the process. That means C2D, right? C2D is the process of heat rejection. That means heat is getting rejected from the system, from the gas here. Let us assume this is the heat rejection. So the efficiency of Carnot cycle can be written as 1 minus heat rejected divided by 1 minus heat added. Similarly, since this is a reversible cycle, we can also write 1 minus T2 divided by T1, and you can do the relevant calculations after understanding this process. Process A to B is an isothermal process. You can apply the first law of thermodynamics if you know the state characteristics, if you know the property values, if you know, that means if you know the heat transfer and the work transfer, then you can easily calculate the internal energy change. Okay, so applying the first law. So for the individual processes, you can apply the first law and do the relevant calculations. Okay, but ultimately you can find the efficiency of a Carnot cycle can be expressed in this format. Okay, so I think uh, okay, after this, let us take a problem, so that what we have discussed till now, this problem will summarize. This problem will try to help you understand. And again, you can deal with the topics which we have been dealing for the last 3 lectures. Okay, so let us deal with this. So let us read the problem first, and then I shall explain why these two drawings have been made. So, a reversible heat engine operates between two reservoirs at temperatures of 600 degrees Celsius and 40 degrees Celsius. Okay, the engine drives a reversible refrigerator which operates between reservoirs at temperatures of 40 degrees Celsius and minus 20 degrees Celsius. Now see, this is your heat engine. This R suffix indicates the reversible heat engine, and you can see this is your temperature. This is your 600 degrees Celsius. I have just converted it into kelvins. Okay, so this heat engine is operating between the temperatures of 600 degrees Celsius and 40 degrees Celsius, and it is driving a refrigerator which is working between the temperature limits of 313 Kelvin and 253 Kelvin. Okay, now the question is, since you can see this temperature and this temperature is same. Okay, so we can say that this this sink can act uh, mm, in a common way. Okay, this sink can act as the source of this refrigerator. That means this refrigerator will take heat from this sink. So we have redrawn it in this format. Okay, so I will explain it now, but just let me complete to read the problem. Um, the heat transfer to the engine is 2000 kilojoule. That means this this is your heat transfer to the engine. Okay, so this is your heat transfer to the engine, that is 2000 kilojoule. So we can write this q1 as 2000 kilojoule. So writing that. Okay, now continue reading. And the net work output of the combined engine refrigerator plant is 360 kilojoule. Now this is your combined engine refrigerator plant. So what happens here? It means that, refrigerator is a device which requires work to perform. Okay, so this heat engine is driving this refrigerator. That means the work produced by the heat engine is helping the refrigerator to work. The work output of the heat engine is the reason behind of the working of this refrigerator. Okay, so this work produced by the heat engine helps this refrigerator to work. Now this W is the work produced by the heat engine, and WR is the work which is consumed by the refrigerator. Now here the net output. So this W minus WR, this W minus WR should be equal to 360 kilojoule. Okay, I hope you're getting my point. And the question is, evaluate the heat transfer to the refrigerant and the net heat transfer to the reservoir at 40 degrees Celsius. So that means they are asking to convert this whole diagram into a problem where it this one this sink will act as a common reservoir for both the heat engine as well as the refrigerator. That means this will act as the sink for this heat engine, whereas this will also act the sink for the refrigerator. But you know that refrigerator takes heat from the low temperature reservoir, whereas it rejects heat to the high temperature reservoir. Okay, so now if you are getting the point, we can say we can easily remove this diagram because it is not of any use here. So this uh, this these two informations have been provided in the problem. Now we need to evaluate the net heat transfer to the refrigerant. Now what is the refrigerant and what do we need to calculate? Can you understand it? The net heat transfer to the refrigerant means, which one is your refrigerant here? This Q3. So you need to calculate this Q3, along with you need to calculate the the sum of Q2 plus Q3. Okay, so these two you need to calculate. So let us first try to find out how we can calculate this Q3. Okay, so how we can calculate this Q3? So from energy conservation principle, you can write this Q3 can be written as Q uh, Q3 can be written as Q4 plus W2. Okay. Oh, sorry. We have considered WR here. R stands for the refrigerator. So you can write Q3 is equal to Q4 plus WR. Okay. Now, you need to calculate both Q4 as well as WR. You don't know these two values. Now there is a relationship which indicates W minus WR is equal to 360 kilojoule. If somehow you can calculate this W, then you will be able to find the value of this WR. Now for this heat engine, you know the efficiency. Remember, it is a reversible heat engine. So eta R can be written as 1 minus T2 divided by T1, which again can be written as uh, output. This is your work output divided by Q1. Now see, you know this Q1. Okay, now you will be able to find this W. So W divided by 2000, right? Because this is the heat input here. 1 minus T2 is 313 divided by, okay, I'm very sorry because I have written 6 instead of 873. I have written here, I'm very sorry, it will be 873. Okay, because it represents the 600 degrees Celsius. Okay, so T2 by T1. T2 is 313 Kelvin and T1 is 873 Kelvin. So calculating this, you can easily find the value of WR. Okay, I'm sorry, you can find out the value of W. Okay, so how you can find the value of W? So calculating this, so after doing the relevant calculations, you will find this W becomes 1284 kilojoule. So it took time to calculate. So it will be 1284 of kilojoules. Okay. So now you have found out, you have found the value of this W. So now you can easily find, the value of WR. Okay, simply if you subtract, so W minus 360 will be WR, and you will find this WR as 924 kilojoule. Okay, so you will find the value of WR as 924 kilojoules. Okay, now the question remains to calculate this QR, because ultimately we need to know this Q3 and we need to know the summation of Q2 and Q3. So we will deal with this Q2 later on, but we are presently dealing with this Q3. Q3 is equal to Q4 plus WR. We have found this WR, so let us write here so that it will be uh, it can be well seen. So WR becomes 924 kilojoules. Okay, so removing the data here, and now let us find out the value of Q4. Okay, so So you can say, you can identify that this Q4 and this WR are related by the COP of refrigerator. Okay, so the COP of the refrigerator, and specifically it is mentioned that it is a reversible refrigerator. So we can write T2 here. It will be, we have we have been used with the word T2, but here you have to see that it is the temperature of heat rejection is mentioned as T4. Okay, so you need to write down T4 here, and it will be T3 minus T4, and ultimately you can write this is nothing but Q4 divided by the work input. Okay, for this heat transfer effect, this is your work input. So you can write this Q4 by WR, and now you know the value of WR, which is 924 kilojoule. So you can write this 924 here. You know the T4, right? T4 is 2, sorry, very sorry, it will be 253, and the difference between T3 and T4 would be 70, because 313 minus 253, okay, it will be 60. I'm sorry again, it will be 60. So it becomes 60. Pardon my miscalculations. It will be 60. And now you can simply carry out a very simple calculation, and therefore you would be able to find out the value of Q4, which you will obtain as 3899 kilojoule. Okay, so you will find the value of Q4 as 3899 kilojoule. Now you know this Q4. Okay, so this Q4 is well known to us. So now our objective to find out the value of Q3 can be easily accomplished. So simply we will add up the value of Q4, which we have obtained just now, and we will add up the value of WR, which is 924 kilojoule, and the answer will be 4823 kilojoule. So now we have found out the heat transfer to the refrigerant. Okay, so we have found out the heat transfer to the refrigerant. Okay, now the question comes, is that now the question is that we need to find out the net heat transfer to the reservoir at 40 degrees Celsius. That means it is, you can see, this is your net heat transfer, right? So this is your net heat transfer. So I am very sorry, I have missed these directions. I have complicated this. I'm very sorry. It will be in this direction and in this direction. Okay, so this is your sink. This refrigerator is taking heat from this one and rejecting to this. Okay, I am very sorry. Please correct this, because I have missed the whole thing, and I did the mistake here. Please reconsider it. Okay, and draw the diagram once. So but the concept remains same. The refrigerator takes heat from the sink and reject heat to the source. Okay, so this remains same. So I have just missed the direction of the arrows. Okay, so this Q4 had become this, and we have found out this Q3, right? Now we need to find out this Q2. How we can find it? This is very simple. You know, from the absolute thermodynamic scale, it is Q1 by Q2 is equal to T1 by T2, right? So you know Q1, it is 2000, it is 2000, divided by Q2, which is equal to T1, that is 873 divided by 313. So ultimately you will get the value of Q2 as 716 kilojoule. Okay, so you will get the value of 716 kilojoule. Okay, so let us write it here. So Q2 becomes 716 kilojoule, right? So now the question was to find out uh, the heat transfer, the net heat transfer to the reservoir at 40 degrees Celsius. That means we need to calculate this Q2 and Q3. So Q2 plus Q3 is the net heat transfer to the 40 degrees Celsius reservoir, and it can be calculated as we have already found out the value of Q3. I didn't write it there, I just forgot, and you will see the result will be 5539 kilojoule. Okay, simply adding up these two, you will get this value. Okay, so with this we have uh, dealt with the first problem. Let us see what is mentioned in the second problem. Okay, now they have said that to reconsider the given efficiency of the heat engine and the COP of the refrigerator are each 40% of their maximum cases. Okay, now what happens if the efficiency of the heat engine and the COP uh, are each 40% of their maximum possible values? That means uh, they are they are asking to consider a irreversible case where the efficiencies will be 40% of the reversible case, because you know reversible engines will provide you the maximum efficiency, right? So now I'm just clearing it up all again, and we'll start it from the first case. So in the previous case, the efficiency was found to be 1 minus T2 by T1. By this formula we can easily find it out. Okay, it was 0.642. Okay, I'm not going into the calculations. You will, I hope you will check it and you will redo it once again in your home, or you are probably doing it now. So if this is your maximum efficiency, then what will be the present efficiency? So let us consider uh, eta A. Eta A is your efficiency for the actual heat engine. So it will be 40%, right? So it will be 0.4 multiplied by 0.642. See, it is quite evident that the efficiency will reduce. Okay, uh, so let us keep it like this. So with this, what will be the change in work done by the heat engine? Previously it was found as W was found as 1284. Now you can again relate the same formula. You know that this, sorry for my bad handwriting, Q1 divided by W is your efficiency. Okay, so you can give a over here to indicate the actual efficiencies. So Q1A divided by WA would be eta A, and I'm very sorry, very sorry. I am just mistakenly, I have written the wrong formula. It will be WA by QA. Sorry, I have been doing a lot of mistakes in this class here. Okay, so WA divided by QA will be eta A. Now you know this one will be equal to, this is predefined and mentioned in the problem as 2000. So this WA can be calculated by multiplying this 0.4 into 0.642 into 2000, and you will find the value becomes 513.6 kilojoules. Okay, so the actual work done can be found as 513.6 kilojoules. Okay, now since we know this and we know this relationship is remaining, it still holds. Now we can calculate WRA as 513.6 minus 360 kilojoule, which will give you 153.6 kilojoules. Okay, it will give you 153.6 kilojoules. Okay, now we have found out all the work done. Now let us try to find out the COP. Okay, let us try to find out the COP. So our ultimate objective is to find the same thing. We need to find this Q2 and Q3 again, but in altered cases. That means now the efficiency of this heat engine has been reduced to 40%, and the COP of the actual case has also been reduced to 40%. Okay, so in the previous case, you must have seen the COP was COP can be defined by this formula, T2 divided by T1 minus T2. So this is your COP for the reversible case, but now here this 0.4 factor needs to be incorporated. Okay, so it gives you that COP will change into 1.69. So the actual COP becomes 1.69. So let us write that. So COP actual, it becomes 1.69. Okay, now the COP or this 1.69, you know that COP is nothing but, COP is what? It is the ratio between this desired heat transfer divided by the work done. So it can be written as WRA. That means the work input in the actual refrigeration case. So COPA, you found it 1.69. You know this WRA as 153.6, right? So you can simply multiply these two and you will be able to find the value of Q4, which is nothing but, after doing the relevant calculations, you will find the value of Q4 as 259.6 kilojoules. Okay, so you have found out the value of Q4. Now you need to find out what is the value of this Q3. How we can find that? You know, simply from the principle of energy conservation, we are doing the same thing, but things have changed. The efficiency and the COP have been changed. So from the principle of energy conservation, Q3 is nothing but WR plus Q4, right? So here I am adding this suffix a, which would indicate the actual case. So now you know this, and you can calculate this Q13 as 413.2 of kilojoule. Okay, now the question remains to calculate the Q2. So you need to calculate the value of Q2, because after you have done with the calculation of Q2A, then only you can calculate the net heat transfer to the reservoir at 40 degrees Celsius. Okay, so this Q2A, again from the energy conservation principle, you can write Q1A is equal to W1A plus Q2A, right? Because this is your input. This input has been used by this work output and the heat rejection. So summation of the heat rejection and the work output gives you the heat input, right? So you can write Q1A minus WA. That has been written by us here. You know Q1A is 2000. You know WA is 513.6, and you can write this value as 1486.4 kilojoule. Okay, so now you have found out the values of Q3 and Q2 when the efficiencies and the COPs have been transferred as 40% of the ideal case. Okay, so now you just need to add it up and you will find the net heat transfer to the reservoir at 40 degrees Celsius. Okay, so it will be Q2A plus Q3A, right? So this is your heat transfer to this reservoir, and this is your heat transfer to the reservoir. So you just need to add it up, and ultimately you will get 1899.6 kilojoules. Okay, so we have completed the problem. I hope you have understood it. It was a very simple problem. We had to use the simple formulas, but it was a you have to move step by step. Okay, you first need to find out what is the unknown, then you need to find out what are the relationships to find that unknown. Like our question was, initial question was to find this Q3. Now this Q3 can be related simply by Q4 plus WR. Now a relationship between this W and WR was provided to you. Now this W can be calculated simply by the general formula of efficiency, and again it was mentioned as a reversible heat engine. The temperatures were provided, so we were able to find the efficiency. Then we just simply related the heat input and this work output in the terms of efficiency. Then we found the value of W. Then after following the relationship of W minus WR equal to 360 kilojoule, we found the value of WR. After finding WR, we know that this WR and this QR, they are related by themselves by the formula of COP. So after calculating COP, we just calculated Q4. So when we were able to find the values of Q4 and WR, we found out the value of Q3. Okay, so this was the way. And again, Q2 can be found out from the absolute thermodynamic scale of temperature relationship, or you can find by this equation also whatever you wish. You could have found the value of Q1 following this as we had already found out the efficiency, we could have used this formula also. Okay, so the formula which we have used in this case, this is somehow the same thing, because it can be expressed as 1 minus T2 by T1. This one can be removed from both sides, which left that Q2 by Q1 is related to T2 by T1. Okay, so this was the process. Okay, same thing was repeated when the efficiency and the COP were told to be 40% of the maximum cases. That means of the reversible cases. Now this is something which you might have confusion to understand. So, but it is simple. Reversible engines will have the maximum efficiency. That is stated by the Carnot theorem. Okay, which we have discussed in the previous lecture. So don't ever forget. Reversible engines will always have the maximum efficiency. So with this, I I will end the lecture here, and I hope the concepts were well dealt with and you were able to understand all the concepts, because the concept of Carnot cycle and Carnot engine and the absolute thermodynamic scale of temperature is very important to solve the numerical problems. So today it might have been the lecture has been lengthened because of the numerical problem. In the next session, we will deal with such three or four problems, and I think in the next class you will be much more confident. You will become much more confident about the numerical problems of second law of thermodynamics. Okay, so looking forward to the next lecture, and thank you. Goodbye.